Today we're going to look at literal equations. A literal equation, also known as a formula, is simply an equation with more than one variable in it. You probably know quite a few. Here's a few that we've done so far in this class. M, the formula for slope, that has 1, 2, 3, 4, 5 variables in it. Y equals mx plus b has 1, 2, 3, 4 variables in it. Y minus y1 equals m times x minus x1. That has 1, 2, 3 variables in it. Here are some other well-known literal equations, ones that you probably know. Area of a rectangle is length times width. Area of a triangle, 1/2 base height. The Pythagorean theorem, most students know that one. Circumference of a circle, c equals 2 times pi times r. Now this one only has two variables, the c and the r. Pi is a known constant. E equals mc squared. That's Einstein's famous formula relating energy, mass, and the speed of light. Okay, in this section, our goal will be to solve a literal equation for a different variable. This means getting the target variable by itself on one side of the equal and all the variables on the other. For example, we might have this equation, solve a equals 1/2 base height for b. The way this is right now, we would say this is solved for a. Notice we have a all by itself on one side and other variables on the other side. So this is solved for a. We want to solve for b, which means when we get all done, our answer is going to be b equals something with other variables on the other side. All right, so how might we do this? Well, what I would do is I would first take this equation and I would multiply both sides by 2. I see an equation that has a fraction. I like to get rid of fractions. So I would write 2a equals, the 2 and the 1/2 would reduce, b times h. Now if I'm trying to solve for b, I notice b is connected to something by a multiply. To get rid of a multiply, I do a divide. So 2a over h equals b, and that would be my answer. We would say this is solved for b. We have b all by itself over here, a bunch of other letters over here, and none of them are b. And that's what we mean when we say solved for b. All right, why might we want to do this sort of thing? Here's one of the best examples I know of. You are taking a vacation in Europe or Canada, or pretty much anywhere else in the world outside of the US. You wake up in the morning and see that the weather forecast calls for a high temperature of 20 degrees Celsius. Everywhere else in the world uses a Celsius scale. We're the only ones who use Fahrenheit. You wonder if you should wear shorts and a t-shirt or jeans and a sweater. A well-known formula for converting between Celsius and Fahrenheit is this formula. Celsius equals 5/9 times F minus 32. So, we know the temperature is supposed to be 20, and we know that's a Celsius number, so we might plug 20 in right here. And then what we would need to do is we would need to get the F all by itself. Well, it's kind of similar to the last problem. What I would do to get the F all by itself is I would start by multiplying both sides by 9, because I have a fraction with a 9 on bottom. 9 times 20 is 180. The 9s would reduce out, and I would have 5 times F minus 32. Next thing I might do is notice that the 5 is connected by a multiply, so I divide it. 180 divided by 5 happens to be 36, equals F minus 32, and then we add the 32 to both sides. We get 68 equals F. So what that tells us is, if the Celsius temperature is 20, the Fahrenheit temperature is going to turn out to be 68. So maybe you want shorts and a long sleeve shirt. Maybe a t-shirt won't quite be warm enough. All right, and then consider the very next morning. So you went out one day, had your fun. The next day they tell you, well, the temperature is now going to be 25. What's the Fahrenheit temperature going to be? And we could do this. We could say 25 equals 5/9 times f minus 32. And then we would have to go through all the exact same steps again to get the f all by itself. What would be better would be to take this original formula and go ahead and rearrange it so that the f is already all by itself at the beginning, and then all you have to do every time is plug in the number. So remember what we did to get this f all by itself. The first thing we did is we said, hey, we got a fraction. Let's multiply by the 9 and clear the fraction. I would do the same thing here. C equals 5/9 times f minus 32. I would multiply both sides by 9. So I would have 9c equals, the 9's would reduce out, 5 times f minus 32. The next thing we did, we had a number here, which was okay. We don't have a number, we have a symbol. We divided both sides by 5. Well, I can still do that. I can still divide both sides by 5. So I'm going to have 9/5 c equals f minus 32. And then we can get the f all by itself by adding 32. We add 32 because that's a minus 32. 9/5 c plus 32 equals f. So now notice how much easier this would be. If I want to know what happens when c is 25, I can just plug it in. So I grab my calculator and I go 9/5 times 25 plus 32, and I know right away the Fahrenheit temperature is going to be 77 degrees. So quite often you're given formulas and you want to rearrange them. You want to rearrange them because you want to know something about one of the other variables, perhaps. So we're going to go through a bunch of examples here. And there's going to be two different types. There's going to be literal equations that do not require factoring. And then we'll turn around and look at literal equations that do require factoring. All right, so here's a good one. Y equals mx plus b. And we want to solve it for x, which means we want to get the x all by itself. Now, what I want you to do is think about what would you do if there were a bunch of numbers there and you wanted to get the x all by itself. I'm sure what everybody would say would be, well, we start by subtracting 2, and then we divide by 3, and we would end up with x equals 1. The fact that we have a bunch of letters here instead of a bunch of numbers doesn't change a thing. We notice we're trying to get this x all by itself. We notice it's connected by multiply and add. When we have multiply and add, we typically do the adding and subtracting first. So we would subtract b on both sides. Y minus b equals mx. And then we notice the x is connected to something by a multiply. To get rid of a multiply, we know we do a divide. So y minus b over m equals x. And there's our answer. That equation is now solved for x. It has x on one side all by itself. It has a bunch of letters on the other side, but none of them are x. All right, this one's a little bit more complicated. M equals y2 minus y1 over x2 minus x1. We're trying to get this x2 right here all by itself. You'll notice back in the previous problems, I said, well, look, we got a fraction. As our first step, let's multiply to clear the fraction. I'm going to do the exact same thing here. I'm going to have m equals y2 minus y1 over x2 minus x1. I'm going to multiply both sides by x2 minus x1. And if it helps, think of that as being over 1. And what that does is it gets rid of the fraction for you. All right, so on the left-hand side here I have m times x2 minus x1 equals y2 minus y1. Now, there's a couple different ways you could go here. Method number one would be, let's distribute the m through. Okay, I'll do that. mx2 minus mx1 equals y2 minus y1. Now, the deal is I'm trying to get this x2 all by itself. I notice the x2 is connected by a multiply and a subtract. Similar to the last time, when something's connected by a multiply and a subtract, we typically do this add and subtract first. So we would have mx2 equals y2 minus y1 plus mx1. Finally, to get the x2 all by itself, we notice it's connected to something by a multiply. To get rid of a multiply, we do a divide. So our answer would be x2 is y2 minus y1 plus mx1 all over m. Kind of a long answer. But again, notice that we have solved for x2, meaning we have x2 over here all by itself, a bunch of variables over here, but none of them with an x2. All right, now I said there are a couple ways to go on this one, so I'm going to kind of do this one again. After we cleared the fractions, we had m times x2 minus x1 equals y2 minus y1. And I said there were a couple ways to go. We decided to distribute the first time and get rid of the parenthesis. Another option would be to get rid of the parenthesis would be do a divide right away. Reduce the m's. And then you would have x2 minus x1 equals y2 minus y1 over m. And then, to get the x2 all by itself, it's connected by a subtract, so we would do an add. So x2 would be y2 minus y1 over m plus x1. And the reason I wanted to do this one two different ways is to show you that if you can do these problems slightly different ways, and when you do, you get slightly different answers. Which one's correct? Both of them. All right? But just watch out for that. So if you're doing it one way and you're talking with a friend, perhaps, and they did it a different way, you might get different answers. Doesn't mean one of you is wrong. Just means you're different. All right, one more of these with linear. Then we'll take a little break, and then we'll look at some nonlinear. Solve. A equals P plus PRT for T. Again, I notice the T is right here. I notice it's connected to some things by some multiply, and I also notice it's connected to some things by some add. When we have both add and multiply, typically we do the add first. So A equals P plus PRT. I'm going to get rid of this P. A minus P equals PRT. And then I'm trying to get rid of this, try to get this T all by itself. It's connected by multiply with two things. That's okay. I can divide by two things. So my answer is A minus P over PR equals T. Now, be careful. You cannot reduce these two P's. You can't reduce it because that's connected by a subtract right there. And we kind of had the same thing in the previous problem. You cannot reduce these two M's because they're connected up on top by an add. So my recommendation here is don't reduce your fractions. In most cases, you can't reduce your fractions. Leave your answer just like that. All right, going to take a little pause, and then we'll come back and we'll look at problems that require factoring.